Hi, and welcome to Advanced Machine Learning. I'm Victor Banks, and today we will start the chapter about online learning, where we will first look at a basic introduction into this branch of machine learning, where we first want to get to know all the basic concept and also have a motivation for considering this learning scenario at all, and later on also look at how do we specify the learning goal in terms of a performance measure. So let's have a short recap on the batch learning scenario, the rather classical way which we consider in machine learning, and try to figure out why it's called batch learning at all. So the name is due to the following fact. So we have typically a data set D consisting of pairs X and Y, feature and label pairs, which are generated by some unknown probability distribution in terms of a random sample. And this data set is nothing else than a batch of data we have. And based on this batch of data, the goal in the typical batch learning scenario is to figure out what is a suitable mapping which is describing the relationship between X and Y. So what is a good model for a given model class or hypothesis space we have. In the sense that we can make good predictions with a good accuracy for data we haven't seen in our batch of data so far. So if we look at this process overall, we can illustrate it as follows, in the sense that we have here two separated phases. The one is the training phase, where we look at our data, our batch of data, and try to find out which model is suitable for this batch of data, which is somehow representative for the learning problem at hand. And once we have found in this phase a suitable mapping, a suitable model, perhaps by empirical risk minimization, we apply it on unseen data in the testing phase. So we test it for our application purposes. But here, one important aspect is both these phases are separated. However, there are learning problems out there, for real-world problems, which don't share this property, or at least they are having some dynamics where a separation is not that obvious. And this is usually coming due to the following facts. So first of all, this is quite different to what we saw before. We don't have a batch of data beforehand available for learning, but rather a handful or no data point at all. And all the data points are only coming or arriving at our system or whatever, at our machine learning algorithm, only bit by bit, in a sequential order. And for these data points, we usually have to do the prediction or the decisions on the fly. So while the new data points are arriving at our system, we have to make decisions or predictions. And this in turn has an effect perhaps on the generation of the data itself, because depending on the context, it might be that the decisions or the predictions we make, they can influence, they can change the data generating process. And there is another important aspect, namely that we have to take into account that we don't have all the time in the world to come to a decision or make a prediction. No, we are quite limited, so we have to do the predictions as fast as possible and additionally, we don't have infinite many computational resources available for making the prediction. We only have limited resources to come to the decision. And this is essentially outlining the online learning world, this realm of machine learning, where you see that we don't have this clear separation of the training and the testing phase, but rather they are going hand in hand in a loop. So we have to train, we have to make use of the data points we have, which is only arriving sequentially, and then make a decision based on what we have seen so far, test the knowledge we have. To have a couple of examples which fit into these dynamic aspects, let's have a look at the weather forecasting example when we want to predict the weather at some geographical location, and we have data available in form of a satellite, where the images are only arriving sequentially, only the recent ones are interesting for making the predictions. And well, here we don't suffer consequences, of course, for our prediction because the weather is quite oblivious to our prediction. But still, the people, and also regarding forecasting extreme weather events, it's important that we make a very quick prediction to react to a hurricane or whatever, so to some weather extremes. Another example in the financial world, imagine you work at a bank, an investment bank, and you now want to make as much profit as possible by investing the capital of the bank at the financial market. So you can invest into some assets, some financial products, and of course these are varying over the time. So again, we only have data arriving sequentially. The most recent ones are more interesting. The decisions we make may have an impact on the asset prices. So if you are working at a large investment bank, and we invest a large amount of money into some asset, this might also have the effect that other banks are reacting to this. Another example are navigation systems, where you essentially try to solve the problem of finding the best route from A to B. And here it's only interesting to look at the current traffic situation, depending on what is going on the streets. One path from A to B might be better than another. And of course, also your decision, if you, have an accident on this route, this will have an implication for the prediction whether the current route you took is the best one to get from A to B. Another example, autonomous driving systems, where you have data coming into your system due to the sensors, the cameras around your vehicle, and while you make a prediction or an action, so to continue driving or to hit the brakes, this will change what you will see or what your sensors will see and give you as the current data points. And what we are essentially doing in online learning is we are playing a game between two players, namely the one player is the learner and the other player is the environment. And the learner is doing an action, which might be a prediction, and the environment reacts to that in the sense that it is providing data. Can be also simply an action if we are in a game playing scenario, so we can also include game playing into the online learning word, then we have that the environment is indeed an adversary or an opponent in a game. And based on the reaction, on the data which the environment generates, the learner should update its internal knowledge, its internal model regarding the dynamics of the environment, take this into account, and then take another action or do another prediction for this game, and in turn the environment will react in the sense that it will provide data or do indeed also an action. Again, the learner will update its internal model, and this process will continue till infinity, or at some specific point it will stop. So we have this game playing view on this learning scenario. And we can also formalize this with these 5 characteristics for online learning. So the one is we have our 2 players. The one is the learner, which depending on the context may represent a forecaster. In the weather forecasting example, may be an agent in the sequential investment example, or decision maker. And the other player is the environment, which also, depending on the context, may represent really an adversary or a user, or even nature itself. And this game between the 2 players is continuing over a specific time horizon, which we will assume to be discrete for simplicity reason. We can also look at continuous ones, but to keep things simple, we will have a look at these discrete steps. And this final time horizon, capital T, this might be a finite integer, but it can also be an infinite. So it can be also infinity in the sense that we are playing this game forever. And the learner has in this game the possibility to do actions, and all the actions are collected in this action space calligraphic A, which again, depending on the context, might be finite or infinite. The environment in turn has also the possibility to do actions, depending on the context, whether it's appropriate to refer to it as an action. Let's say it's providing data, and this data is living in the so-called environmental data space, which we refer to calligraphic Z. And in order to learn something, to make learning possible, we will assume that there is a loss function L, which is mapping an action A of the learner compared to an environmental data point Z to some real-valued number L of AZ. It's representing how good or how bad the action was for the environmental data point Z, which the environment provided. And we have the following mechanism. So it's a loop, looping over these discrete time steps we have here. So let's assume we are in iteration number T, or time step T. And then what we have is the following mechanism. First, the learner is choosing an action from all the available actions, in order to emphasize that the action taken in time step T, we will have here the subscript T at the action A. The environment in turn will react in the sense that it will generate data, an environmental data point ZT in the available environmental data space, and the learner will then see this environmental data point and compute the loss, which is then taken into account to update the model, to learn whether the taken action AT in time step T was indeed a good idea regarding the data which was generated by the environment. So the typical scenario from a machine learning point of view is the following, where we have that the action space, calligraphic A, and the environmental data space, calligraphic Z, are both corresponding to the label space Y, so that we have here the following correspondence, namely the action of the learner is indeed a prediction, so it's a Y hat T, so it's predicting a label for some machine learning scenario, and the data we obtain from the environment, from nature, whatever, is indeed a label, so a YT which we wanted to predict. And there are, of course, different ways then to have a meaningful loss, depending on what the label space is, whether it's a discrete label space for classification or continuous for regression case. We know then what types of losses we can consider. Then you might wonder, well, this mechanism is quite simple. Is it really possible to represent every online learning scenario we can think of? No, that's why it's the basic online learning protocol. You can extend it. So you can play around here, of course, also with the order, whether the environment generates the data beforehand, or it will generate a part of the data before the action is taken. And this is the extension we will also consider here. Namely, we will assume in some cases that the environmental data point consists of two parts, ZT1, ZT2. The one part is revealed before the action is made by the learner, this first part. And the second part, accordingly, is only revealed after the action or the prediction of the learner is done. So we have then the following adaptation of the mechanism of the basic online learning protocol. So first, the environment generates the data consisting of the two parts. The first part is obtained, is observed by the learner, and then only the learner chooses an action, and after performing the action, the remaining part of the environmental data is revealed as well, so that the loss can be computed in order to figure out whether the taken action was indeed a good choice or not, which will lead to an update. And of course, it's reasonable to believe that this additional part, so this first part we have before we do the action, should be taken into account when making the action. And this is the extended online learning protocol we are looking at here, which is in the machine learning world typically instantiated as follows. So again, the action space for the learner is the label space as before, but now the environmental data space Z is the Cartesian product, so the typical data space in machine learning applications, so that the first part is then the feature information we have at some time step t, some information about the weather in some neighboring location, for instance, or the current situation at the financial market, whatever. And then when we want to predict something, the weather in terms of the temperature, this is then the YT, which we want to predict as accurately as possible with our action AT, with our Y hats, which might depend on the XT, so on the feature information we have, on the additional information we have about the environment. And what else is quite different, or usually quite different in online learning? Well, in the batch learning scenario, we typically have the assumption that the batch of data is an IID sample, from some unknown probability distribution P. But this statistical assumption is usually not made in online learning. So you usually assume nothing at all at the generation of the environment data. So you can also have the case that the data is generated by some adversary. This is also the reason why typically no statistical assumption is made. Because if you want to model the game learning scenario, then it's quite unnatural to assume that there is a probabilistic law behind that, but rather that the adversary is doing some strategical thing in the sense that the data is generated such that the loss should be as large as possible for the learner. But of course, you can also have a statistical assumption on the data generating process, but then you usually don't have stationarity or something like that, because the dynamics of the data is changing over the time. So you have concept shifts or drifts in this process. Recall, we have the consequences if we make predictions in some cases, so that the data generating process will perhaps change over the time. And in order to make online learning work, we have a couple of requirements. So we have to think of how can we specify a good online learning algorithm. And well, obviously we have to take these dynamical aspects into account when we design an online learning algorithm. So this means on the one hand, we have to cope with this problem that we only get the data bit by bit, so that we don't have a large amount of a pile of data before we start learning, that this data pile is only getting larger over the time. And if it is getting larger, we have to keep in mind that it might be the case that we don't have all the time in the world to do an action, to make a prediction, but we rather have time and computational constraints, so that the update, so the prediction for the current time step should not depend on the time, but rather something like the complexity of the action space, the dimensionality of that, something of that kind. So we want an online learning algorithm which is having cheap updates, so that we can have some incremental updates in this way. All right, although this is quite important for the online learning case, that we don't have all the time in the world and do not have all resources in the world, we will only look at these implicitly, in the sense that every time we construct an online learning algorithm, we will talk about whether it is time and memory efficient, but the measure we will use for the theoretical analysis, this will only look at the more or less the performance of the learner, in the sense that it's tracking the cumulative loss. Because it's rather difficult to incorporate these time and memory constraints into one single number. So it's rather something like a multi-objective thing, but still then the time and memory constraints are not that easy to incorporate. So the measure we will look at is the so-called regret, which is given as follows. So first of all, let's recall our scenario that we have a learner which is generating a sequence of actions, and we have an environment which is every time reacting to that, or if it's oblivious, it will simply generate data. And what we can do now is, well, for all these pairs, we can compute what the loss is, A1, Z1, and so on. We can do this every time and then accumulate everything. And now what we can ask for is, well, if we would have used, instead of A1 in all the cases here, if we would have used simply another action throughout the time, an action A, what would have been the cumulative loss in this case? And we can compare the difference between these two things. And this is the idea behind the regret we see here, which we measure with respect to some competing action A, where we think perhaps, well, the A would have been a good action, so let's see whether this is indeed the case and compute the cumulative loss in hindsight for choosing this action throughout the time. So again, the first part here, this is referring to the learner, the cumulative loss of the learner, and the second part, this is the cumulative loss of some competing action A. And well, we could ask for what is the best action in this regard, in the sense that we look for the one which is having the smallest cumulative loss. And if we compare now this cumulative loss with the cumulative loss of the learner, we would end up with a suitable measure for the quality. So again, we compute the cumulative loss of our learner and compare it with the cumulative loss of the best action in hindsight, in the sense that we look for the action which would have generated the smallest cumulative loss if we would have used it for all data points or for all time steps ranging from 1 till capital T. And if this value here is small, very small, then it's telling us that the decisions which our learner has done were indeed good. If this value here, this difference between the two, is large, then obviously it's telling us that the learner did a quite bad job in some sense. And this value, this is the regret. So why is it a meaningful name? Because we can also look at it for every time instance separately, and what we are essentially then measuring is the difference between the taken action and the best action, and this difference can be interpreted as a regret at that time step. So we regret that we did not choose this best action in hindsight, perhaps. And there's an obvious relationship between this regret, if we have this infimum in front of this second sum, and this regret we saw before, the regret with respect to some competing action A. Simply the following: this regret is nothing else than the supremum over all possible action when we measure the competing, the regret to the competing action A, yeah? Because supremum, we can here flip it with the minus here in the difference to an infimum, and we have the equivalence here. All right, and the objective for every online learning algorithm will be to minimize this cumulative regret. And one additional remark needs to be done here. Namely, it might happen that this cumulative regret is negative. Yeah? For instance, if we have a couple of time steps, where in fact the losses we suffered with the taking action of the online learning algorithm, yeah, so these AS here, are smaller than the losses of the best action in hindsight. Yeah, so the action which would minimize the cumulative loss in hindsight, this A star here. This might happen. And if this happens too often, and we look at the cumulative difference between the two, yeah, we end up with the case that this regret measure which we had, which is the sum over these AS, and we subtract here the loss of this best action in hindsight. If this is happening too often, it might be the case that this here is negative. But usually this will be not the case. Yeah? So in the typical scenarios we will consider, we won't have the case that this is happening too often and the best action in hindsight is already doing quite a good job, in the sense that one fixed action would have been already a good idea to choose throughout the time. This will be reflected by the fact that the cumulative regret will be non-negative, usually. And then if we have this case that the cumulative regret is non-negative, the objective we have here, that we want to minimize the cumulative regret with our online learning algorithm, this boils down that the regret is sublinear with respect to the time horizon t. And why is this a good assumption or a good goal? Well, this sublinear in the time horizon t, this is telling us that the regret of the online learning algorithm for the time horizon capital T is a small o of t. So we can rephrase that as follows. So if we divide on both sides with a time horizon t, this is telling us that the regret divided by t is O of 1. Yeah? So it's a sequence which is going to 0 if the t goes to infinity, if the time horizon goes to infinity. But if we break down what this regret divided by t is, well, what we see, it's nothing else than the average regret we have per time. No? So we compare here the losses of our online learning algorithm with the best action in hindsight, and then we divide it by all entries we have, and these are t many. So you see, this is in fact something which we want, which is desirable, that the average regret per time step goes to 0. This is why this sublinearity in the time horizon is indeed a good goal. But you might wonder, why are we simply comparing with a fixed best action in hindsight, which we called A star, and why don't we compare with the best sequence of actions? So where we ask in every time step what would have been there the optimal action. Well, the first reason is that this best fixed action in hindsight, this is already a quite hard opponent, so to speak. So if you compare it with the batch learning word, in the batch learning word you would indeed also consider the same or a similar problem. So if this A is a model, the S are your data points you have. What you do in empirical risk minimization is you look for the best model inside your model class, if A is the model class, which is minimizing the cumulative loss. So this best action in hindsight is, from a batch learning point of view, well motivated, because you're essentially doing the same. You are at a time step capital T, when the game has ended, you're asking for what is then the best action, which might correspond to an entire model, the best model in hindsight in some cases. Of course, taking into account that we have these dynamical aspects in the online learning world, where we don't have this typical fixed data generating process where it is evolving over the time, this best action in hindsight as the competitor is perhaps too optimistic and not the best way to go. And we could, of course, then simply replace this best action in hindsight, A star, with the competing action sequence A1 star, A2 star till A capital T star. And then measure the regret, again compare essentially cumulative losses between the taken action of the learner and this sequence we have here. The A1 star till A2 star, which might be the sequence which is minimizing in every time step the loss, which would be a quite hard competitor, of course. If we would do this, we would end up with the so-called dynamic regret, which is of interest currently in research and also has been analyzed theoretically what in the sense what good online learning algorithms would be for this case. But in this lecture we will look at the static regret, because this is already a quite hard competitor which we consider there, namely the best action in hindsight, as we will see. And usually the ideas you have for this static regret can be reused somehow for minimizing the dynamic regret as well.